Okay, please join me in welcoming Mariana.
So thank you so much for the invitation. I'm very happy to be here. As I already mentioned, I've been talking to you the past 2 days. I'm a senior forecaster at Nixle, and today I want to talk to you about StatsForecast. I think all of you already know StatsForecast. It's our open source Python library for statistical and econometric forecasting models. We're very happy that it's one of the most used forecasting libraries in the field, with over 20 million downloads and more than 4,400 GitHub stars. And in this presentation, I want to give you a look under the hood and explain to you what makes StatsForecast a lightning fast, scalable, and state-of-the-art library for time series forecasting. At the beginning of this workshop, Rob gave us a very comprehensive overview of the last 25 years of forecasting software. And as he mentioned, for many years, R dominated the time series forecasting field with packages such as Forecast, which was later replaced by Table. And back then, there were some Python libraries that offered some of the models in the Forecast R package. Today were usually slow and difficult to scale. So to address this challenge, Nixle developed the StatsForecast. And the main features that we'll go into detail in this presentation is that it's lightning fast, scalable, it's easy to use with the well-known pick and predict methods. It's an accurate implementation of the forecasting models, and it's fully open source, and it remains to stay that way. Let's get into the architecture of StatsForecast and what makes it so fast and scalable. StatsForecast is lightning fast, and as you know, since many of you are developers of these forecasting models, many statistical models such as ARIMA and ETS can be very slow, especially on large data sets, or in very specific points, like when you're trying to compute, you're trying to do maximum likelihood estimation. So to overcome this challenge, the StatsForecast initially employed Numba, a just-in-time compiler for Python. What Numba does is to translate Python functions just decorated with the just-in-time decorator to optimize machine code at runtime that can approach the speed of compiled languages such as C and Fortran. And I have a little example over here. This one. Here's a very simple example, but I think that showcases why we initially started to use Numba. Here I'm just summing the elements of this array. And when you have the same Python function, but you add the decorator, then you have a significant speed up. There's a delay when you do the first run. I mean, there's on the first call, the improvement is not that big, but it's still significant. So this is why we first use Numba on StatsForecast, and it gave us some good results. But obviously, there's no free lunch. Maybe Numba can have some downsides. I just showed you the cold start issue, and obviously it requires some additional dependencies. So for this reason, we also created Forecast, a library that implements several operators in C++ to transform time series data with the possibility to use multi-threading. And the basic structure in core Forecast is the group array that is two NumPy one-dimensional arrays, one for the data and one for the indices. So let's say that you have a series, a time series of 5 observations and one of 10 observations. So in the data array, you're going to have all the observations, and the indices, you will have 0, 5, and 15, which will determine the start and the end of each series. So this has helped us improve several of the models. We have used this in ETS, ARIMA, all the Theta models, and there is not a need for you to use core forecast directly, as StatsForecast uses it under the hood. Well, the title of this presentation is StatsForecast under the hood, so what's there is, well, one of the things is core forecast. Now, the StatsForecast is also designed to be scalable. It can use multiple cores and machines or servers. You can do parallel execution, that's on single machine, or you can do a distributed execution across a cluster. StatsForecast can use multiple CPU cores. You just simply need to specify the njogs parameter when initializing the StatsForecast class. If you set it to greater than 1, then it's going to do parallel processing, and setting it to -1 is going to use as the available cores in your machine. So if you're forecasting, say, 1,000 time series, instead of taking 1,000 units of time sequentially, you can process them in a for loop, in finishing 250 units of time, no? Assuming that you have four cores. StatsForecast is also compatible with Spark, Rake, and Dask through Fugue. Spark, Dask, and Ray are two of the most popular frameworks for distributed computing in Python. And Fugue is a unified interface for distributed computing that lets users execute Python code on top of these frameworks with minimal code changes. And Fugue was developed by Han Wang, who recently became a Nixlab CTO. So we're very happy to now have him on board. And well, to run forecasts on Spark, Rake, or Dask, you simply need to pass the corresponding data frame to the StatsForecast methods. With minimal changes, the StatsForecast will automatically detect the input type and use the corresponding distributed engine to execute the task across the entire cluster. And it's just all of these elements, the number just-in-time compilation, the C++ that is in core forecast, together with the distributed computing, is what makes StatsForecast lightning fast and scalable without any loss of accuracy. We have some empirical results using the M4 competition dataset. For the Ultra-RIMA, we had experiments using the daily, the hourly, and the weekly dataset. In terms of accuracy, I think it's comparable with the R version. It's slightly faster in some cases, and it certainly outperforms PMD, ARIMA, and Prophet. This experiment was done with Prophet still was very popular, but well, obviously it cannot compete with neither of Nixlab or R. And we also have the same results now for the ETS. Again, I think in accuracy is comparable to R, and in terms of time, sometimes it's considerably faster, sometimes maybe a little bit slower, but the accuracy is very similar. And I think in both cases, that's models that used to be the dominant Python implementation, but that one is really left behind because it takes way longer and is not as accurate as the other two. So we recently also incorporated support for polars. So we tried to make StatsForecast as usable to everybody as possible. And well, with that being said, let's get into the models available in the StatsForecast. We have tried to create a very comprehensive suite and to be a faithful and robust implementation of the models in the Forecast R package. We currently have 9 families of models, or 35 models or methods. We have the RIMA, the ETS. For multiple seasonalities, we have the MSTL. We have our own implementation of TVATs that follows the R implementation. We have the classical models for sparse or intermittent series, the baseline models like the naive or the seasonal naive. We have several variations of the theta model, and of course the models for forecasting volatility, GARCH and ARCH. Well, we're very happy that 2 years ago, Rob mentioned that the best implementations of his continuous methods were available in Ixla. I don't know if he still believes that. I hope so. And recently, we're very proud that StatsForecast was implemented in the Python edition of forecasting principles and practice that is fully open source, and that Rob and Azul already mentioned. I was surprised to notice that yesterday the first edition wasn't included. I think I've never seen it. It's like a rare Pokemon card, but well, there it is. And the core methods of StatsForecast are the fit, the predict, the forecast, cross-validation, and plot. And I would like to emphasize the difference between the forecast and the fit and predict. The forecast is supposed to be memory efficient. It does not store partial model outputs and is compatible with distributed engines, while the fit and predict does store the parameters for every model, but they're not defined for some of the distributed engines. So it is a trade-off. I mean, if you want to have the result as much as possible, use the forecast method. If you need some of those parameters, then use the fit and predict. All the models in the StatsForecast are local in the sense that they're applied to each series, unlike the global models that are available in our other library, the neural forecast. And well, they're local in the sense that they learn the patterns of each series individually rather than learning from the complete dataset. And it is very easy to use a StatsForecast. You simply need to pass a pandas or a polar data frame, or if you're using Spark data frame, and you just need these 3 columns: the unique ID, the unique identifier of the series, the timestamp, and the target column. And I would like to now spend some time talking about uncertainty quantification in StatsForecast. I think that's an important topic. I think we usually focus on point forecast, but the StatsForecast also offers probabilistic predictions, either via analytical formulas that rely on some distributional assumptions, simulations, and from version 1.6 or higher, it also uses a conformal prediction. So the analytical formulas are based on this formulation. We use, well, the point forecast plus minus a critical value corresponding to the desired coverage probability. So if you have taken a statistics course, then you know that for a 95% prediction interval under the normal distribution, then the critical value is 1.96. And then you need to multiply the critical value times that the forecast varies. For some models, it is easy to get the forecast variance. For some of the ETS models, there's a explicit formula. So what StatsForecast is doing in the background is to implement these formulas. And we use Rock's other book, the Forecasting with Exponential Smoothing, to implement the prediction intervals in these models. However, as he and his co-authors mentioned in this very same book, there's no analytical expression for some of the models. So in those cases, StatsForecast is going to use a simulation. We use 5,000 future sample paths, And then we compute the prediction intervals from the percentiles of these simulated future paths. Unfortunately, StatsForecast doesn't tell you which algorithm you are using, but if you, for the ETS models, if you check Rock's book, then you can see which models have an analytical expression for the forecast variance and which don't. And as I mentioned before, from version 1.6 and from version 1.6, we also have conformal prediction. That is a distribution-free uncertainty quantification framework. How it works is that we first feed the forecasting model to the historical data and then compute the residuals. And then we compute the prediction interval using the empirical quantiles of those absolute errors. So they're given in a similar way. It's just that instead of using the critical values and the forecast variance that rely on that normality assumption, we're going to use the empirical quantiles of past residuals and the absolute forecast error. Let me give you a quick example so you can see how to use conformal prediction. It is also very straightforward. You just need to, define the intervals. In this example, I'm using their passengers data set. And to use conformal prediction, you just need to specify the forecast horizon and the number of windows. This number of windows are the ones that are going to be used to compute the residuals and then the quantiles that define the conformity scores. And then you simply pass these intervals to the models. And just as before, you put just as in other cases, you just need to specify the levels, and these are the conformal prediction intervals. And now I would like to show you a complete workflow using the BM1 competition data. I think this is a good example that shows the ease of use of StatsForecast. It also gives us the opportunity to show you the recommended pre-processing that we use. And then it also showcases the accuracy of some of the models in StatsForecast. So let's go to this example. I think some of you are already familiar with the PN1 competition datasets, but for those of you who are not or don't remember the specific details, this was a competition that Nicolas van de Putte and others organized last year. It was basically Twitter data looking like this, and the frequency of the data is weekly, assuming that the weeks start on a Monday, and the goal is to predict the next 13 weeks. So here I plot some of the series. The one in pink is the actual values that the participants need to forecast. And just as I already mentioned, the output StatsForecast needs to be in this format: the unique ID, the timestamps, and the target value that in this case represents sales. The BM1 competition use a very specific score that it's kind of like a combination of the mean average error and the bias. It is computed calculating the absolute errors and then subtracting the errors, the absolute value, and dividing by the total sum. And the top 5 solutions obtain these scores. This table is important because we're gonna return to that soon. And here's a very simple workflow that has proven to us to be very useful. We recommend it a lot, and it's just for very easy steps. First, you need to check for missing values. In this case, well, there are none, but this is an important step because StatsForecast cannot handle missing values. Then we need to check for missing dates. That is very easy to use with this function that comes from another of our libraries, the field gaps. In StatsForecast, the series can have different start and end dates, but for each series, it is important that there are no gaps between in that time range. But in this particular case, all the series ended on the same state. So again, in the competition, there were no missing dates, but something that it was present was leading zeros, and we recommend removing that, especially in when you're dealing with retail data, because that usually that left tail usually brings the forecast down and it makes the accuracy worse. Obviously, this is very this depends on your use case, but I would recommend that you do consider removing the leading zeros if your data set has some of them. And finally, our last preprocessing step is to identify obsolete series. Basically, for the series that have no sales in, say, the last 180 days, just assign a zero forecast. Again, obviously, please consider your context, but at least in this retail example, I think it's a very reasonable thing to do. Obviously, this is very arbitrary, but again, considering the context, I think it's a good filter. And for this example, we're going to use all these four models: the AutoRima, the AutoETS, AutoComplex Exponential Smoothing, and AutoTheta. And again, to use StatsForecast, you just need to instantiate the StatsForecast objects, defining the models, the frequency, this parameter, we'll talk about it. It's going to use all the available cores in my computer. And in case one of the models fails, so you always have a forecast, you can pass a fallback model that in this case will be the naive. So we're going to generate all these models, and then we're going to take the media. This combination actually was proposed by Kostas Petropoulos and Ivan Tantinkov. I think it placed 6th overall in the M4 competition, and it placed 2nd in the weekly category. And I think it's a good combination. There's been a whole research on sample models. I particularly like this combination because each model captures different things. The ETS is used on weighted on weighting the past of the observations. ARIMA captures the interdependencies. The complex exponential smoothing focus on nonlinear term tendencies, and the dynamic optimized the dynamic optimized theta model employs short-term curvatures and long-term trends, and actually performed very well in this competition. I think the second place used some version of theta, again also in an ensemble. And just as a quick note, as I mentioned before, I said, if you want to use, say, Spark, you just need a minimal change. And yeah, the only change needed is you need to, instead of a Pandas data frame, to pass an Spark data frame, and StatsForecast will automatically recognize this input. So once the forecast is already computed, it's going to take around 2.5 hours on this computer. obviously, if you have a better one, you have a cluster or access to cloud computing is going to be faster. But here I'm just creating the example that is the median of these four models. And then since these are retail sales, then just set, everything that is smaller than 0.01 to 0. And from the last preprocessing step, set the obsolete zeros to 0. And with that result, well, with that, we obtained this result, 0.5328. We can also see the performance of all the other four models from the four. The auto theta was the best performing one, but I mean this still is not that great of a result. The naive was also in the competition, and the naive got a score of 0.5. But something that can really help in this situation is to use a hierarchical approach. I think in this workshop we have discussed a lot about hierarchical reconciliation methods, and we can use it in these data sets. The idea is going to be to use the same ensemble, but now at the client level. The data set have three columns: client, warehouse, and the product. And obviously, the combination of all three is the target level and is the one we just forecasted. But now we're going to do the same StatsForecast ensemble at this client level. So the series of when you add them up, they have a higher level, but some interesting patterns start to emerge. So well, here's another example where there's some clear seasonality, and you can also see some well-defined trends. If here I'm just generating the same models, doing the ensemble with the median, and setting the forecast for the obsolete series to 0. And well, these are the results. They look reasonably well. And the next step is gonna be to do the hierarchical reconciliation. That is gonna be based on forecasted proportions. I think several of you are really familiar with this idea, but for those who don't know, we basically gonna use the forecast at this level, say 120 units, and then we're gonna splash it to the products using the forecast for each product that was done at this level. So, for example, say that this client only has two products, A and B. Say that the forecast at this level was 50 units for each. So Fetopol is 100, and each is gonna get 50%. And the upper level forecast at this client level is gonna be divided 50%, so 60 units. And just I should have added this, but this is obviously done for all the warehouses. I mean, this is the target competition level, the product warehouse client level, and this is the client level. That is considers all the products in all the warehouses. So if here I decided to implement the reconciliation manually, but obviously a more efficient way is to use directly our hierarchical forecast library. But I wanted to do it manually to show you just this small edge case. In the case where the base forecast is 0, obviously the proportions are also gonna would be 0. But in the case that the upper level forecast is not 0, then we are simply gonna divide it in equal parts. I mean, in this trivial example, since we have two products, then it will be half. But well, just with this hierarchical reconciliation method, now we have a forecast at the target level, and our score now significantly improves. Now it's 0.4943, and I think that the results look reasonably well. You're probably wondering, well, how would that have performed in the competition? So let's see. And actually, it will have placed 6. The actual 6th place was 0.4962, and ours was 0.4963. So we will have placed 6. That is just out of the money prices. But well, it's still. I think it's still a good result, and I think it showcases the ease of use of StatsForecast and the accuracy of the models. And this is not it. And just to wrap everything up, I want to emphasize that StatsForecast is open source and will remain that way. StatsForecast is the work of a lot of very talented people, and we welcome your contributions. If you want to report a bug, if you want to help us by fixing a bug, you have some feature requests, or you want to add to the documentation, or even add a use case, please do so. We have a detailed guide on how to contribute, but it's actually very easy. You need to clone the repo, set to clone the environment, install the dependencies, and that's it. You just open a new branch from main to do your changes, and then you can push your branch and open a PR. And well, hopefully in this presentation, you learn what makes StatsForecast lightning fast, scalable, state-of-the-art, and well, we are committed to keep it open source.
Thank you.
Oh, thank you. And the argument of that some cases you showed in the accuracy metric, because I know the code well. I studied report of, and you show some improvement compared to our forecast, because it is identical, and really the code is identical. The only part is different from R is in ETS or R inline uses or R stat packer. So optim packer or optim function in R, and next day is using, I think, new implementation uses the optimization from icon. And do you know the difference, and what could be the reason? Because our optim package is quite efficient and have been proven for years. And do you know what is actually happening?
Yeah, I mean, obviously we're limited to the optimization available in Python. We try to make a reliable implementation of the models in the forecast R package, but obviously some differences are inevitable, and I think that's why we try to emphasize that the accuracy is similar. Obviously, in some cases, is gonna be worse than the R version. In other cases, is gonna be better, but on average, is very similar. And I think that what we try to focus also is in how fast it can be, and that is the result of several things. You know, the number used, the C++ implementation, then all those alternatives for distributed computing.
And another question, what was the reason to have a C++ backend? Because you claimed that Numba reaches the speed of C++ or Fortran, but although the initial version was developed by Azure, it was only using Numba. And what made the decision, because it is extra effort to maintain a C++ package and then another package. And
Yeah, I mean,
so let me find.
sorry.
It doesn't mean that Numba is not as efficient as Python community claims, or was there another reason?
No, nobody is efficient. It's just that, as I mentioned here, it's not free lunch. I mean, it comes with some additional dependencies. Obviously, I mean, you have the cold start issue, and the decision to move everything to C++ was mainly to avoid those additional dependencies. Of course, creating now this core forecast library will now forces us to maintain it, and obviously requires extensive knowledge of C++. So it's definitely a trade-off. I think in the future we're probably gonna move to core forecast, but well, we always try to make it as fast and efficient as possible. So, but yeah, I mean, to be perfectly honest, is something that we decided to do, like during that development that obviously involved several developers.
Yeah. And in case of when you're building the model objects, that object we have model that if some model goes wrong, we have naive forecast as a
Yes, the color.
Yeah, default one. Is it reported if there is any error? And because I would like to know what happened.
No, yeah, of course. And to be honest, I think someone opened an issue. I mean, that is a limitation of StatsForecast. Now that you mention it, it's going to go up the priority list. But no, I mean, you will have to generate a naive forecast and then compare it to your other results to see if the fallback model was used or not. And it is a big limitation.
Because if I always have, I don't know, a user misspecifies something in the model that initially, if all models are naive models, I mean, I would realize it, all of them, but most of them are only naive models. And also one suggestion can be, when you're creating this hybrid forecast, you could take an instant flow. So cross-validation and use this weights and try to, I mean, division models could also have and have a division, of course, each time series are long enough to do that. Next to that.
No, yeah, I agree completely. I think that with this example, we just wanted to showcase the ease of use and the accuracy of the models. But of course, I mean, using the median is very reasonable because you discard extreme results. But you can also use cross-validation and get weights for each model. So for each series, maybe you have a weighted combination of ARIMA, ES, SES, and PICA. And then for another series, you have a different combination. But yeah, it can be done. And maybe with that, you can now get into the top 5 and get one of the money prizes.
And
I don't know if we have time. I have two questions. One quite fast because it's the line of the Numba and C++. Since Python 3.14, it's supposed to have a native cheat compiler and will continue evolving, I guess. If it's the case, are you planning to stop using Numba and use the native compiler, or
Yeah,
you have something in the Roma?
we StatsForecast uses the icon wheel for version 3.13. There's no support yet for this new version, but certainly now that is now available, we'll probably research it and then decide. So yeah, that is probably like in the near future.
And my other question is that about conformal prediction. It's like hot topic. But working with that, I think maybe I'm wrong, just write me, but they are only guaranteed to actually coverage for one step ahead. And most of the cases, forecasting more than one step ahead. And it doesn't guarantee that coverage for any step ahead, and the error, it's not being propagated. So that it's constant, the interval, and find a way to solve, well, I guess not to solve, but try to refit.
It's just that we compute the conformity scores, and then we use the point forecast. So the prediction intervals are not necessarily like straight lines, because you are using the point forecast plus the plus or minus this conformity score. And
But that's a constant. The conformity is the plus or minus is constant. So if you are 10 step ahead, you are creating an interval that it has the same width.
I understand now.
There is not that expected error that you know what's through.
I mean, there's an H subscript. Yeah. There's an H subscript on the error. So the H step ahead error, it's not unstep ahead. You could get the error on switch to H. So it does give error at times.
And from where do you change that error? Have you done like any from a consolidation set? Will you save like in a different bucket the errors for which end stacks?
Yeah.
And what if you predict more stacks that you have?
Yeah, then you will get repeating in the process. And this okay. Yeah. Which is be the problem. Up to you, let's see.
But that is why when you define the conformal prediction, you need to specify the forecast horizon and the number of windows you want to use.
And inject the receivables of frame 5 testing. Right?
Yeah, I mean, you this is done automatically. You get the prediction interval. You just need to specify that, and you get the conformal prediction intervals.
It's not going to work for the large patch because you're not going to be able to compute residuals for large patch.
I mean, essentially, you're just running constantly off on like your new sample data. So it gets super data hungry really fast. Because you need a lot of windows and then you're just running a lot of cross validations in the past.
Okay, thanks for the great discussion. That's all we have time for. So please join me in thanking Mariana.